class is going to be on your work and work energy principle. Okay, so if we consider just a particle or an object and it is being acted by a constant force, let's say the force is some force F in the x direction, and due to this force the particle is now going to move along a straight line. Okay, the situation is that we have an object of mass m. It's sitting on this planar surface, and we are applying a force. We are applying a force in certain direction, and this object is going to move along a straight line. Okay, so the position that the object is going to move from is position 1 to position 2, and by definition we say that the work done on this object or particle is defined as the dot product of your force times your displacement. Okay, so let's take that the displacement is delta x, and it is happening along the I direction, which is the x direction. So the force can be decomposed into the three components in the x, y, and z direction, and the value that you will get for this dot product will be your force in the x direction, the displacement in the x direction, and the cosine of the angle between these two vectors. Okay, so that is the basic definition of what is work done on an object. Okay, now we write work done as W, and displacement can be anything. Sometimes people use D, sometimes X, so that can change. And the units of work is in SI is Newton meter, and in compact form it is also known as joule. Okay, so the first statement that we want to understand is that work is done on an object when the external force acting on it will displace it. Okay, if there is no displacement, then the work done will be zero, right? Because the force times the displacement will be zero. Okay, you might have encountered the example, if I stand and start pushing on a wall and I am applying a lot of force in pushing a heavy wall and the wall is not moving, then the displacement is zero. Okay, and in that circumstance I might get tired. We have to ingrain this concept of what is work and what is energy and how they are different from each other. Okay, so work can also be positive. It can be greater than zero, and that would mean that this force and displacement have to be in the same direction. So if you are applying a force and the displacement is in the same direction, then you can say that the work done is going to be greater than zero. If the force and displacement are in opposite direction, then the work done can be less than zero. So you can have all the scenarios. Work can be zero, greater than zero, less than zero. So we have to look at the specific case that we are dealing with. Okay, and a situation might be a little bit complicated. You might not have one force, you might have more than one force acting on an object, and in that circumstance what we have to do is we have to calculate the net work done. Okay, and net work done will be the net force times the displacement of the object. Okay, let's look at this example. Okay, so we have a person, and this person is carrying a suitcase, right? And the question is, what is the amount of work done by this person while he's carrying the suitcase? The person who is holding the suitcase, right, he's applying some force, and that force is in a contact force because he's carrying the suitcase, right? So if there is gravity acting, so there is a force of gravity on the suitcase, and it is balanced by the force that the person is exerting on the suitcase in the opposite direction. So when the person is moving along this straight line, this direction of motion is 90 degrees to your application of force by your hand. And so then the dot product, which is the magnitude of the force times displacement times the cosine of the angle, which is 90 degree, will be zero. And similarly, if you think about it, if there is a satellite, okay, and it is orbiting the Earth, all right, and now it is going in a steady orbit, so we can ask the same question again: what is the amount of work done to move the satellite in this circular orbit. All right. And even in this case, since the satellite is moving in the circular orbit, there is a centripetal force that is applied by Earth. Okay. So now the force and the direction of motion are at perpendicular 90 degree to each other. Okay. So then the work done will be the dot product, and that turns out to again to be 0. So until now we have discussed that the force that is acting on the object is constant, right? However, if you think about it, that is rarely the case, right? Even if you consider a simple case where a person is pushing an object on sitting on the ground and there is friction, you will realize that the force is not actually constant, right? So if you try to push an object, initially there is no force that is acting on the object. Okay, so the applied force is initially 0, and then slowly if you start pushing the object, then because of the frictional force, the object initially won't move, right? And the more force you applied, the more frictional force that is developing in the object will oppose the motion, and finally you will reach a point where the applied force is more than the frictional force, and then you will see the case where the motion will start happening. So in scenarios like this, the force actually is not constant. Okay, and for the cases such as spring force and your gravitational force, these forces are also not constant. They can vary, right, depending on the position of the object with respect to the earth, or depending the position of the object that it is doing oscillation. We cannot just use a dot product. Okay, so we have to think about the force as something that can vary with time. Okay, and then in this situation, when there is force that is a variable force, that it is not a constant, it can go up or it can come down. And now let's say we have the same situation. This force is causing certain displacement, and you are moving the object between position A and position B. And now when you look at this situation, you cannot just look at an instantaneous point in between these two endpoints A and B and say that that is the work done in moving the object. Okay, so what you have to do is you have to look at the area under the curve, and that entire area under the curve is your work done. Instead of looking at the instantaneous value of the work, which is your limit of this delta x tending to 0, that you're looking at just a point where the force is acting, or just a small blip in the time scale, right? You're looking at the entire process that it takes for moving from A to B. Okay, and to compute the entire area under the curve, what you will need to do is you will need to use the integral function. Okay, and so then the definition changes a little bit. Then in a general way, we can say that the work done on a particle in moving it from some position A to position B will be this line integral of A to B, and it will be an integral of force times dx. Okay, and this f now is not just any fixed value, it is a function. Okay, dx is what is your displacement. So when you take the integral from A to B, that is the endpoints, that will give you the work done on your particle when you're moving from position A to position B, right? And like we were mentioning before, if you're looking at just a small point at any instant in time, what is the work done? That will just be dw, which will be f of x dx, right? And then you integrate both the sides, and then you can find the complete work done between some endpoints. And the example is of the spring. So we have a spring that is oscillating back and forth about its equilibrium position. And like I had mentioned, if you notice, the force that is exerted by the spring is not constant, right? So that is represented by this red arrow, right? So as you can see, the arrow is increasing in strength and decreasing in strength, and that is basically telling you the strength of the force and the direction. Okay, so at the center point, because there is no acceleration, there is no restoring force, and it's 0. And at the end points, you will have the maximum restoring force that is exerted by this spring on this object. Okay, so it is not a constant force, it is a function of the position. And in this scenario, suppose we want to find the work done by the spring in moving this object of mass m. Okay, so we know the force that is exerted by the spring is minus kx. Okay, and now if you want to find the work done by the spring in moving between any 2 points a and b, then we can use our integral form, and that will be an integral a to b, and you will have f of s and dx in the integral. Okay, and then you can substitute for your f of s value, which is minus kx. So you will get a term of minus kx dx, right? And k is your spring constant, it is constant, so it will go out of the integral, and a negative sign can also go out, and so you are left with integral of x dx, which is just x square by 2. Okay, and now that you have to evaluate between the endpoints a and b, so your expression will be minus 1/2 k b square minus a square. Okay, so that is a simple way of calculating the work done by spring by using our general expression of the integral. So the important theorem that we want to discuss is the work energy theorem. Okay, and it is a very useful theorem, and it will be applied in cases where we are trying to solve some numericals or trying to simplify a difficult problem. And by definition, as you remember, work done is just integral of a to b times your force times your dx, right? So this is my value for my work done. Okay, now when I want to equate it to energy, I have to remember energy is something different, right? Energy is the capacity of an object to do work. Okay, so any body that is in motion, right, it will possess some kinetic energy, and the work energy theorem relates these two concepts. Okay, so we know from Newton's laws that F is equal to ma, right? Or you can write it as m dv by dt. Okay, similarly, we know that velocity is your change in x by change in time, so dx by dt, and that means that dx you can write it in the form v dt, right? So if I substitute these expression in my formula, I can write it as a to b, and I have m dv by dt, that is for my force, and the dx is v times dt. Okay, and so my dt can cancel. Okay, and you have your integral a to b m v dv. Okay, so now you have changed the integral limits from basically your position to your value for velocity. Okay, so essentially what you are saying is that when you're integrating this, you're integrating at the limits of some velocity at point A to some velocity at point B. Okay, and as you know, we can take mass as constant in our classical case, and then we are left with v times dv, and this is nothing but v square by 2. So you get v square, and then now you have to plug in the value for the end points, which is va and vb, and so you get an expression in terms of 1/2 m vb square minus 1/2 m va square. Okay, and that is nothing but saying that you have your kinetic energy at position B, which is 1/2 m vb square minus kinetic energy at position A. Okay, so this expression here is your expression for your work energy theorem. Okay, and just by looking at this equation, you can tell a lot about what is happening in the situation, right? So if I look at a situation where an object is moving and the kinetic energy is increasing, that means the kinetic energy at B is greater than kinetic energy at A. Okay, so then the net work done will be positive, right? And if an object is slowing down, that means the kinetic energy at B is less than kinetic energy at A. That means my net work done is negative. Okay. So in some of the textbooks you will see that kinetic energy is written as T instead of Ke. So you should not be confused about that. It's just a way of writing the energy, because we usually use E to represent the total energy, and you will see T used commonly as kinetic energy term, and V as in Victor to be used for potential energy. Okay, that the net work done by the total force, okay, acting on a particle is equal to the change in the particle's kinetic energy. Okay, so all you care about is the kinetic energy at the second position and kinetic energy at the first position. That's all you need to know, and then you can find the work done in this situation. Okay, in this example we have an object, okay, of mass m. It is moving from this position A to position B. Okay, so that is what it is doing. Only gravity is acting on this object, and what we want to do is we want to use the work energy theorem to find the expression of the distance. Okay, so let's assume that the distance between the points A and point B is h, okay, or the height that the object is moving. Okay, and what we are saying is, let's assume that the final velocity is 0, and let's assume that the initial velocity is something that we don't know, but it is not 0, so the object is moving. First we will define that, let's take this movement in this direction upwards as the positive y direction. Okay, and there is no movement in the x direction, so we don't need to consider that. Okay, so then on this object there is only one force that is acting, that is the gravitational force. Okay, and the sign for the gravitational force will be minus mg, right? Because if this is the positive direction and gravity is acting in the opposite direction, so then you have to include a minus sign here. Okay, and then the net work done is just the gravitational work, because there is no other work acting on the system, no other force. So your work done by gravity is minus mgh. Okay, and we can use the expression for work energy theorem and say that this work done minus mgh will be kinetic energy at B position minus kinetic energy at position A. All right, and we know that at position B the velocity is 0, so the kinetic energy at B term 1/2 mvb square will be 0. So you are left with only the second term, which is minus times 1/2 m times v a square. Okay, the velocity at position A, and then you can equate both the sides. There is a negative sign, it will cancel, the mass gets cancelled, and then you can find the expression for height, which will be va square by 2g. Okay, so it's a problem where previously you could have used just the kinematics equation and solved it, but in the simplistic example we can use the work energy theorem and solve the problem as well. And later on we will do much more complicated problems where we will have friction and other things taken into account as well. All right, suppose I change this problem and I say that the object is at position A, and I would like to move this object, and I hold this object from position A and move it to position B. Okay, so in that scenario initially the velocity was at 0. Okay, the object was just sitting here, and then I moved it to this final position B, and now again the object is stationary. So now in both the cases the velocity is 0, so the change in kinetic energy is 0. So essentially when I move an object from a stationary state to another location here, the net work done by me and the gravity combined is 0. Okay, so I will probably do plus mgh amount of work, gravity is doing minus mgh amount of work, so the net work done will be 0. The distance x is the distance covered by a particle is given by this expression. Okay, so it is a function of time, and we have to find the acceleration of the particle. Okay, so we know that the acceleration of the particle is d square x by dt square. Okay, so first thing first, let's calculate dx by dt. Okay, and that would be your expression 8 times 3 times t square. Again, all you have to remember is if you are taking the derivative of any function raised to n, then you get nx raised to n minus 1. Okay, so that's all we need to remember. You have 8 times 3 n and x raised to n minus 1, so you get t square. Similarly, here you will get 6 times 2, and then you will get a value of t, right? And then you will get 4 times 1, and the last one is the constant, so you get 0. Okay. Then you can calculate d square x by dt square. So again, this is 8 3 is 24, so you get into 2 times t, and the next term will be 12 times taking the derivative of this with respect to time, so you just get 1, and the last expression is 0. Okay, so that is your expression for acceleration. Okay, so 48t plus 12 is your expression. All right, and let's see the question again. So the question is saying the acceleration of the particle, is it remaining constant, is it increasing with time, is it decreasing with time, or to choose the second option, that as the time is increasing, your acceleration is also increasing. Second one, again, you have to do the same idea. You have to calculate the velocity. That means you just have to calculate dx by dt, and you have to do it at time t equal to 0, right? So all you have to do is you have your expression 4 minus 5t plus 8t square, and if you take the dx by dt, so first term will become 0, you get minus 5. So I can just write here minus 5 plus 16t is what you will get as your velocity, right? And now you have to do at t equal to 0. So then this term will go, and you are left with minus 5, right? And that is your answer. So the last one was the problem. It was the tricky one, and most of the people got it wrong, right? So a body can have 0 velocity and finite acceleration, right? So it's a simple case. You have a of an object like this, and let's say I kick this object, and it is going in something like this path, and when I kick this object, and from a field, of course, whenever the object is at any position, there is gravity acting on it, right? So at any point there is gravity acting on this object. Okay, and suppose I throw an object straight up in the sky vertically, right? So initially it will have some velocity, right? So that is initial. When it reaches the highest most point, then the object will have 0 velocity here. Eventually the object is going to come back down, right, and fall on your head if you don't move. Okay, so now you have a situation whenever the object is in the air, there is acceleration due to gravity acting on it, so there is a finite acceleration. However, at the end point, the velocity can be 0. Okay,